Okay, we are recording. All right, so last time we were building our own pet system. I don't think we got all the way through it though, if I remember correct. I think we at least got, I think we got through the mesh grid part. Is that where everybody else has on theirs? Yeah. That's what my memory says anyway. So anyway, this is where we are up to now. Now remember, we're doing, there's kind of two stages, right? You have to, this is kind of building the fake R system part. And there's enough complexity to this one as opposed to in the past when we want to do like a CT, we could just call on MATLAB's radon, right, to do a radon transform. If that command didn't exist, we'd have to write our own radon transform. That's basically where we're at here. We need more than a radon transform, right? We need something that actually allows radioactive decays and all kinds of other stuff. And then once the radioactive decay happens, then it needs to do a radon transform in both directions and then check and see if it was actually received and then cancel it out. Just so it fits within a reasonable time period, we said we weren't going to worry about the absorptions since the vast majority of these, being very high energy, don't tend to get absorbed. It is rare. In a large number of counts, it does happen. So in a real system, you would have to worry about it. It's, you know, the majority of them will make it through, but some won't. There are other noise factors that can come into play on this as well. But we're going to stick to small and a simple system, and that'll remove a lot of those complexities. And again, for a first time, it's good enough for what we've got. So this is where we had gone from last time. Maybe it's a good idea just to run through I'll go back up and we'll show where they all came from real quick. All right. So again, we had kind of two things. We had the emission spectrum on the right. We got the detector rings. The red line is, you know, a line between two particular detector pairs, and there are different sources it could have come from. Concentrations are on the one on the left, and the absorption information is on the one on the right, and we said we're going to ignore the absorptions. So we just made this basic framework, right, that went in. I also had commented that by putting those comments right underneath it, it makes a help file for you for free automatically. You know, then we just measured IG as the geometry, which we're going to ignore, but IG, that's kind of the right side picture box. IC is the left side box that was in there. You know, if we wanted to be really fancy, we would get the rows and columns of both IG and IC and make sure they were the same and so on and so forth. But we're not really worried about that one here. And if you notice, I only put a few of these in, right? I did the first four, I left the last two. Just as a note, when you're done, add the last two in once you understand exactly what distance and debug are. So you can expand it. And we should really have a description of what this does before this, make some commentary, add your own description of what you think would make, you know, be a quick thing to tell you what does this thing do. The title is fairly decent, but, you know, the make pet, but away we go. So we said we needed to calculate where the detectors were. That was the first step we had identified. We just reminded ourselves of the geometry, and we're basically looking for all the pairs going across between these, but the detectors are evenly spaced. So for that one, we just calculated what was the radius. You know, there's several different ways you can do it. I picked my radius for this one to be basically the minimum size necessary to hold this image, basically. A real physical system would actually be a little bit larger than that. There'd be some dead zone area. But again, simplifications. The rest of this is being able to figure them out, right? So, you know, the detector, the angle between them, we just took 2 pi divided by number of detectors. Then we set up basically the XY positions of them, which we just evenly spaced radius, cosine, and sine. And we just got all the positions. That's kind of standard picking points on the outside of a circle stuff. So that should hopefully not be too fancy for them, right? Then we needed to find the center of the image because the mesh grids should be equally spaced around them, you know, and get how big should the columns of A be. You know, as a note, we also know the rows of A too. I probably should have put that in here, but I dealt with it later. You know, and then we just set up that A and the mesh grid. And we mentioned that the rows of A should be equal to basically all the measurements that you got. So, and that's what we ended up on this one, right? So we had this capital N here, we will actually define later on when we get into them, but it's, you know, the length of I just had to do with how many of the voxels we have to go through, and this N is the number of those detector pairs. So if you think about that one for a sec, if I'm going to get a fairly decent resolution inside somebody, I'm going to have a lot of detectors on that outside ring. Right? Because if I have, say, like 100, I can only do a 10 by 10 box. So you will really need a lot of detectors. It shouldn't be too surprising, though, if you've got, like, say, a meter, you know, diameter system that's on there. I would need to have an awful lot of detectors. Otherwise, if they're fairly big chunks, you're only going to be able to get that much of a resolution. You know, and this is just, you know, find the rows, get the standard, kind of divide them up, and that's the split here. Important just to notice we did the -1 because of MATLAB refusing to number intelligently from 0. And then note on the top of the next one, we just also have the setup to walk through all the detector pairs. All right, so we, you know, have one detector as the start, the other detector as the end. And that for the one that's doing the end detector, since we're walking through each one in turn, you don't want to repeat and go the backwards direction. So we start the end one from the one after the current start. So we just walk through the start ones in sequence, and they're so far uncounted end pairs with them. All right. So that's pretty standard setup of a lot of programs that goes on. So I think this is where we're at, and I had asked everybody to try to think on the idea, you know, how do I find the voxels on a line from the D start to the D end, right? And I'll include this one on here again so you just think, you know, I've got, say, for instance, D start up there and D end. How do I know that it's these? And have we done something so far that would help me with this?
Well, with ARC, we did a very similar thing. We just need the angle of the line and the radius is small straight.
Yes. How wide are you going to consider within this line that if the center is there, we call it part of it, right? And then we need to know how far it is from the isocenter and what angle it makes. Knowing the start and end detectors, can I figure out the angle? Yeah, I've got the XY positions of them. So it's pretty straightforward to figure out an angle once you know the XY positions. Right? That's just kind of standard geometry stuff. You know, yay for arctans and that. Right? So I can get those, the XY differences, and I can get the angle pretty easy. How do I get the radius? How far we're offset, or whatever you want to call that. The distance from the center to where this line is. I should be able to figure that one kind of out, knowing those same X, Y positions, and this is the dead middle, we've already kind of calculated the dead middle. Right? So I should be able to kind of stick it in that basic line equation and use you can use the delta XY positions and figure out what that minimal distance is based on that, the center point, which you already know where that is. We calculated that previous step. All right? So once I have those, I've already got a mesh grid that holds these position areas. I can just use the standard line equation we've used so far with that tolerance. So it looks almost exactly like what you did twice now, right? Once for, we did for FBP, and then we did it for art/BIM. So I guess you could call it 3 times if you want, but we just, for art to BIM, it was a pretty direct conversion, so it might not be as much attention, right? But it's that basic same mesh grid line calculation that you've done, depending on how you counted 2 or 3 times. Right? Hopefully that lets you see there are a lot of codes that are very similar. So if you understand some basic ideas, there's some very good ways you can reconstruct them and reuse certain functions. Right? So try your best to take your code from those others, you're calculating the line, get your angles and your offsets, and then we'll take a look at how I calculated mine. So where's everybody at?
I think I got angle and offset. I'm just doing threshold right now.
How about other people? Where are we functionally at? You got an idea where you're going?
A little bit.
Okay, well, I mean, you got your linear equation set up for it, comparing to your distance off of them. So, which is to remember, right, your angle is now gonna have to be something you're gonna calculate. And you'll calculate from that earlier stuff that we did, where you got the positions, the XY positions of the detectors, and you now know detector numbers start and end. And you have a list of XYs. So how can I get to an angle for XY?
we've got a circle, and we've got pre-calculated points, right? I'll just get some on the opposite side. All right, so if I know this one's the start, I can identify that maybe this one's the end. I can get the XY positions easily, so dx, dy, right? Dx, dy, and just use that index to look in. Same thing here, right? I can do the x of d start and dy of d start. Right, now I've got the xy positions for each one. That means I, in essence, can take between that xy position and I can calculate the delta x and the delta y. Right?
Yep.
So how can I figure out an angle?
Are you gonna take the cosine of the y for the x?
Okay, so if I do the ratio of the x and the y, is it going to be cosine?
Sine.
So if this is the total distance across, which is, 2r, right, twice the radius, how do we define cosine?
It should be tangent, right? Or tangent.
Right. So tangent is your x over your y. So to get the angle, you want a tan of that ratio. And that ratio is a difference between your xy positions.
Okay.
Does that make sense?
Yeah.
So break them into small little bits. We're going to reuse, like in a lot of your engineering, a tan comes up in disproportionately huge amount. Even when you're calculating control systems, I'll probably asked this before, but I never remember. Has everybody had controls or not yet? If you ever have to do controls, grad students usually take a linear system. It's a good one to take anyway. But even as an undergrad, at some point you should take controls. When you do controls, one of the things you have to do is convert between your normal space to this kind of polar space, which is really what you're doing when you're doing a Fourier transform. Since Laplace is an extended Fourier transform, it's going to implicitly have that same functionality. So to go back and forth, it involves a tan. It's the same ratio. So when you're going to a phase space to reconstruct things, and that is naturally the way in which the universe works, because calculus, the fixed point of it is exponentials, which generate sine and cosine. So in some sense, that's the natural way the universe expresses itself, in terms of equation-wise. Which means all of your mathematical descriptions, when we go to solve them with the calculus problems, at some point will involve a tan, because you'll get that ratio of tangent. And it's better to do a tan in most cases than sine or cosine, because it's more likely that x and y are going to be similar in size than x and whatever the radius is for it. So it's going to be less sensitive to numerical noise in your calculations. Measure your scope.
I have about here. So like this part. Literally what you
That's why, and you got your data.
Yeah. Now I'm just.
You're actually doing a smart thing down there. So you calculate your radius.
Yeah, I
in
use
this.
this.
Yeah.
We did
Yeah.
it in robotics.
Yeah, you'll see these carry overs all the time. Okay, now you know. Remember that rad, and just make sure you don't reuse a name anywhere else, because we tend to rad here. So just call it something else, like off or something, or rad, whatever. That's telling you when you're calculating that line. Remember when we're doing our line distances, we created a mesh grid.
Mm-hmm.
And that mesh grid had an implicit center. So the distance from the center to your line is that offset. Right? And since your mesh grid has that implicit area, everything else has to also. And we centered that other one so that the center of that image matches up with your circle. Right? So when you take a look at the equation for finding a line, it's, you know, it's got basically the B one gives you basically that distance that's on here. You know, and I forget what we called it on the other one. We call it distance or offset or radius or something from it. But it's basically how far is your line from the center. Right? And then we just had our, you know, using the angle, we can calculate sine and cosine, and away we go. I'll give everybody a couple more minutes. Cheers, good, Stephen. You kind of came in late, so.
Yeah, I'm just trying to follow along.
This might actually help. I'll go back to the previous one. It might be helpful to you, but just, that's the code we've already got. So it might just be helpful to get the previous code in there. Because we're gonna test it when we're all done. When you think you've got something, let me know. Good. How about you guys? Good, a little bit longer.
But yeah, I was looking at the art, so it's kind of like this equation, which is exactly what we did in the art, right? You do this less than distance, but we don't have to go.
Because that's how far are you gonna accept? If I'm off, right? And so for instance, you could pick that as a half, 0.7, right? Because no line is gonna perfectly, what you're calculating there is the center point of that voxel.
Yeah.
Is it on the line? Right? Well, it doesn't have to perfectly go through the center for it still, right? If you took this and considered it broken up into, let's just do a simple 8 thing, right? I would still call this one that's going through here, even though the center is still off, right? So this distance here, that's what that, you know, what's called dist in our thing is, right? And it's basically telling you how far from the center is good enough, right? And it goes on both sides, so it's going to measure. So the dead minimums you'd want is 0, because that, or sorry, half, which sets this up, right? And then 1 over root 2 gets you this. So somewhere between a half and 0.707 and change is about the size you want that distance. But we just set that as a parameter. You can pass it in and you can try different things to see what works for you. Okay, well, it sounds like you're just worried about parameter sizes. Is it good if we take a look at the actual code then? Or at least the code that I wrote, and we can see if it works similar. Okay, so this is what I did. Right, you can see in the first two, that's basically what I said. Calculate your delta x and your delta y. Right? You know, calculate your theta from a tan of 2. That's fairly straightforward. Why not just a tan?
Domain restriction.
Yeah, the regular tangent in mathematics is defined specifically just on area, whereas a tan 2, right? So tangent actually takes just a single number going in, which is the ratio. A tan 2 takes both basically the numerator and the denominator, and it looks at the signs of them to figure out the quadrant. and then it does tangent, but then knowing the quadrant, it does the appropriate phase shift to get it the actual correct angle. Then I just calculated the delta there that's a weighting factor, right? So in theory, for most of our stuff, that should be 1 for most cases, right? When you're breaking them up. But if people pick up different sizes of them, this one will, if you have bigger sizes, it normalizes it appropriately. So we should really account for that, just in case, you pick a weird ratio, because we do allow you to pick fewer or other things, so the spacing between them could be really big, and we want to normalize it so we don't get some funny scaling off of it. So that's what the delta is there for, and you'll see that we have, like when I calculate my radius, this is potentially the only thing that might be different on yours. When we put it back in, it's expecting us to have that radius normalized to whatever it is. Otherwise, I've made false circles, right? The bigger ones will change it. So other than that, it should be what you expect, right? If you remember the change in x times the dy and the dy times the dx, basically, the difference between those divided by that normalization factor gets you how far away from the point is. And that's just the equation for the line and using our dx, dy normalized inside our basic line setup. And then from that, I'm calling A temp the result of mine, because I'm trying to make a row of A, and I just need scratch space to hold it. So this will be a single line. I cast it as a double because otherwise I might not get these. Some of these are logic functions, but we don't want logic. We want actual double precision numbers. So absolute value, and that's just the equation you had before, right? Our radius minus ax times cosine minus ay times the sine. That whole quantity, right? Take the absolute value, because I don't care if it's left or right of center, related to distance. If it's within distance of the center, we call it good. This marks up all the squares as either, yep, it is within range, or no, it's not. So they all get 1s or 0s, and then it's turned into double precision, so I can do calculations. Then don't forget to reshape. So that's one that sometimes gets people, is they forget to do the reshape to turn it into a single row. And then I put it in a row. That's why I started here, row 1, because it's MATLAB and they have to start at 1. And then I just say, hey, great, I just did a row, so increment my row counter and grab the next pair and find out, mark all the ones in between them. So this is basically exactly what you did before, except we're going to build the full A matrix here. Wasn't that really bad before? Didn't we just do the A matrix just in time?
Yeah.
Yeah, so but this time I'm building the whole dumb thing and storing it. Why is it okay now and it wasn't okay when I was doing art?
It's gonna be a lot smaller.
Yeah, this one's going to be a lot smaller because I'm only going to have the number of my rows be proportional to the detectors times detectors minus 1 over 2. Whereas before, it was proportional to the number of histories total that went in there. That's more proportional to the count of them. There'll be a whole bunch of counts that get binned together on this. So.
I have a quick question.
Yeah.
So I did the radius calculation a little differently. I assumed that the midpoint of any chord on a circle is the closest to the center. Is that correct? Like if you have a circle
Point.
and you connect any chord on that circle, is the midpoint of the chord closest to the circle?
It should be.
Okay,
Yes.
that's how I did it. So I just-
Yeah, it should work out the same. As long as you don't have some weird scaling in there, you should be good. You know, it should be actually true for any point along the line.
Okay.
So that's why when I picked mine, I just did the start. So you pick the actual end, but any point along that same line should have a effect of, you know, basically having no offset, right? So that's, you know, that line is the null space. I guess is another nice way to say that. So it should be the same. I just did this because less calculations. So, if there are errors though, mine potentially could be more error prone. So there's nothing, because I'm further out on the edge. If the errors are proportional to the distance from the center, and sometimes they are, then it would be worth going back and calculating. So I'm taking a little bit of a risk to reduce my calculations. All right, we good? Okay. So now what I wanted to do is I want to put in, that's technically it, right? I put my A matrix. I'm actually done what I wanted. However, I've noted in the past there have been, this is one of those things that a lot of people get wrong, and it's hard to know you get it wrong until you do the reconstruction. Right? So what I want you to do is to do a couple, I've created some options for debugging. Right? So you now know what distance is for your commentary because we stuck it in here. Right? So your commentary from the distance should go up here. Now we're going to do debug. Want two debug options. Right? Debug option number 1. Right? You're going to draw the detectors and then you're going to draw a line between them. Right? So that's going to let me see basically every spot. I'm not drawing the width of the whole line because then you won't see anything. If you get too many detectors in here, you still won't see anything. We'll pick a smaller number. But you should get these kind of beautiful weaving patterns, basically, that'll show you, if you see a red line, that tells you that thing is solidly covered. Wherever you see gaps, that tells you that's potentially where there could be a little bit more error, you know. Where they all overlap, you'll see some circles and you'll see some gap circles. That's where potentially also you can get the ring artifacts. So this will make a nice thing. If it doesn't look perfectly symmetric, like a beautiful little line drawing pattern, like weaving of some type, if it doesn't look like a really neat woven thing, then you calculated something wrong, right? And you can see where there are gaps. Sometimes people get weird gaps, like they miss one at the beginning or the end, and all of a sudden there's a nice pattern and then there's like a missing line, which tells you, oops, off by 1, I missed the detector when I was counting through it. So that's kind of what option 1 does. It just makes sure you've got all the pairs correctly. What option 2 is going to do, I want you to show a temp before you reshape it. Right? And make it so that you can walk through them. So you basically have to have it so that you can just like hit a key to go to the next one. So what in MATLAB allows you to hit a key and it just keeps you there until you do it?
Pause.
Pause, right? So just do pause. So you're gonna actually image show, right, this particular function, and you'll do a pause. Make sure you can't do option 1 and option 2 at the same time. Because to do this combo, see how option 1's in 2 different places? You're going to have to draw it and hold it till you do the update to draw on the other lines. Since the other one's in between, you could theoretically grab the handle pointing to that figure and then call the figure back up, make it active, then hold it, and then redraw. But yeah, I'm being lazy. Do either 1 or 2. The neat thing you can do with option 2 on this is if you're walking through it, you'll actually see, for instance, I start mine on the left if you're following my code. So you'll see something that looks like, whatever, and then the next one, it'll erase that, it'll give you the next one. And you'll see all these pairs one at a time. It'll walk through and, as you do them, it'll move to the next one. So you can check and see if it skips something or misses them. You can just be walking right through and see, is it good, is it not good? So those 2 ones
have found the majority of people's errors. So I found them to be good debugs, and they also give you characteristic types of debugs. So it is nice if you have a somewhat complicated function to get debug levels. And the number that you put in, like 1 does option 1, 2 does option 2. And in your comments, you should explain what those are. Make sense? So make your attempts at these debug codes. And then I'll show you how I did mine. And of course, it's MATLAB, there's a million ways to do it, so I'm just giving you one option. So those are your showing. The existing code. Hey,
But, trying to understand the mesh group.
So remember we did the same exact thing for FBP and ART and BIP. We created a mesh grid to find out which one of this. The mesh grid is basically the grid of our pixels we're going to reconstruct on. Right? So these are basically, in our case here, it's the grid of what were the concentration blocks. We're looking for concentrations of our radioisotope. And that one, we always center it, right? So all medical imaging thing we use is an isocenter right in the middle of it. So we took, for our system, we basically found the center of our system. Right? So IG was the geometry description. How many rows and columns did it have? Well, that's that's the boxes that we want to look for. So we basically found halfway inside the box, which is the middle of the box. And we went, equal number of boxes left and right of center. Left is negative, right's similar. Right? So that's all we're doing on that. We're just creating a grid that we now know what are the coordinates of those boxes inside our space.
Okay.
So when we go to calculate the line later, this is just the equation of the line, right? But we can use AX and AY, the grid center locations, are just contained within that mesh grid. That's what mesh grid makes. It makes the grid that has all your center locations. So it just makes for really nice notation inside your MATLAB.
Sure. So you're referencing, so correct me if I'm wrong, so like the mesh grid is making like to allow you to index the
Basically,
grid without.
it's
actually
indexing,
noticing
it's indexing the XY coordinates of the center of every grid point, of every little grid square.
okay.
Right, so let me scroll this back, or actually I can use this one here, right? The mesh grid makes this, right, this is my detector. This is the boxes, and inside these I'm gonna put the concentrations of the isotopes, that's what I'm trying to solve for. Mesh grid basically gives you the XY coordinates of every one of these dots. That's its whole. That's the XY center for every one of these. And it does the X and AX, and it does the Y and AY. And it actually stores them in this nice little grid-like pattern. So I can do simple calculations and it hits everything in there without me having to for loop through everything and whatever. It's just designed to be a fast, easy way to do it. It is memory wasteful as hell, but it reads elegant. And MATLAB would care much more about the elegance of the read than the efficiency of the calculation. Because if you're trying to write efficient code, what are you in MATLAB for anyway? That's wrong tool, But it's the right tool for developing the idea. Then you can take the code from here and figure out how to write it efficiently. Okay, do we think we have debug stuff? There, awesome. So this is what I did. Yeah, it's not hugely fancy, right? I just checked if the debug level is 1, that was option 1. Open a figure, plot the dx and the dy's, and I put red stars on the ends. Right? You don't want a line type there, otherwise it'll draw lines and you'll never see where the detectors are. So, I mean, you could pick, there's a lot of things out there. The stars I find particularly visible when I look later. And making them red just kind of makes them stand out. That's all to hold on. That fixes and freezes that so I don't have to worry about it again. The corresponding spot on the other side, when I'm inside the loop, drawing the line between start and end, right? I just again check, is it 1? And if it does, I just plot a single line, right? The dx of the start, the dx of the end, dy of start, dy of end, and I made it a blue solid line. Again, that way I know everything along where I'm measuring exactly on that line. Right? Similarly for debug level 2, it's really easy, right? I just debug to image show my current A temp. I calculated the previous line, and I just put pause. And just lets me do the key presses. At this point, the only thing that I have to do is set up, I've now got kind of my A. I'm supposed to return both B, right? And what is my concentration vector, things of that sort. So what I need to do for that, right? I need to set those up and then go through all the pairs in each box to calculate B for concentration and time, right? What that really means to get that B, right? So B is your measurements. Right? B is along all those lines because it's 1 per row, and a row is a detector pair combo start end. Right? I have to basically walk through
for every pair start and end. There's a whole bunch of boxes along those lines, which I now have enumerated in A. Alright, so for that row, I know which ones they are. So I can walk through a row in A and see 0, it's there, 1, it's not. Alright, so I might have to walk through those. I don't actually have to do the start and end if I don't want. I can just walk through those particular ends, but I do have to know where the boxes are located, because each box has a concentration. That's the IC. Right? Notice there's a time period T to them. Right? So this is how many of the time periods go on. And what we're going to do is use the basic Poisson equation. Right? So we're just going to take the Poisson area. We have the concentrations are basically proportional to your lambda, basically, right? And for each time period, right, the Poisson equation will tell you how many decays are, kind of expected to happen. The number of decays that happen, you just do it for each one, and then you find out that's for each combo towards a detector pair that gets them. And we just add all those up for everyone along the line. So if there is a 1, right, inside of your particular row of A, you're going to go in and go, oh, take the Poisson equation and calculate the number of ones and add it into a running total of B. You do that for every single box along the line, boom, you've now got exactly what you need for it. So essentially use your ICs as your lambdas, and then T as your time variable, right, for how many periods. And remember that the probability equation for your Poisson distribution is for one time period. So how many time periods, it's a pretty straight multiple, right? That's basically the idea of that happening on. So that's going to be the measurement. That's what the detectors on the ring detected. So now that we know the paths who might contribute to a detector's measurement, we've got to do the Poisson calculation to find out how many did they actually get. Yeah. Does that make sense? Awesome. So take your best guess from that one. And sadly, this is when I was originally doing it, I was thinking, oh, that's where I get my detector pairs. Because I just wrote my code and then I dumped my code and I worked backwards and deleted stuff. And I was thinking, oh, this is where I want to talk about the number of detector pairs. And I forgot it also had to do with the size of A. So this is where we're going to calculate N for A. So we talked about before, right? This is just like number of detector pairs minus 1 over 2, because we don't care what direction. That's all that's pretty good. Once you know that N, that's what you can set the for loop for. It just walks through all the A's. Good. So, give your best spot. If you don't remember what the Poisson equation is, then you can just write it without that knowledge. Or take a quick look on Wikipedia and see. We did mention it last time. I don't know if I actually put the equation in. I drew the picture, but I didn't. I didn't give you a Poisson formula. But you can, I'll give you this. If you didn't know what the Poisson formula was in getting the mean, you could quickly look it up on Wikipedia if you needed. Or it was on the two or three slideshows back, the one that was on the nuclear. We talked about the Poisson equation there. Whichever makes you happy. Or just write, your expected Poisson decays times the time period. And I'll give you the equation in a few seconds here. How are we doing? We need a little more time. See how everybody's got. We'll compare them to mine. Like I said, and it's exactly what I said, right? Half the textures times. For this one, I had two different things I'm gonna do, right? One, I just did a concentration, which I see that's coming in, is gonna be an image. Concentration is just reshaping that into a single vector, because everything I've got is in vectors. I don't wanna re-box them and unbox them, so I just vectorize the concentration. That's all we're doing with it, right? It's just to make my calculations easier, so I can walk through an index. Otherwise, I either have to undo A into this one's form, or I've got to take this one into that one's form. So that's all I'm doing with concentration. So I walk through all the pairs, and I'm gonna walk down every box that's in it. So that's just whatever the length of I is, however many columns in A there are. Right? And I just check and see if A for that particular pair and that particular box is bigger than 0, that means it's 1. Right? That means I've got data for it. If I've got data for it, and when I take a look at the concentration, which is just the IC reshape, there was something in there. Right? If there was no radioactive particles in it, even though it's along the line, there's nothing to calculate, right? So is the box on the line, and was there something radioactive in the box? That's what I'm asking on that if. And if that's true, whatever B was for that pair, because it's row by row, I just plus equals, but I can't plus equals, so I have to do equals B again and plus. This is the actual simple calculation for it, right? Easiest thing I can do for Poisson, you could actually put the formula in yourself, or you could use the fact that MATLAB has Poisson random, which is a Poisson random variable generator, and all you have to do is feed it your lambda, and lambda times t, I remember lambda is the parameter, and we said the concentration is our lambda value. So that times t will give you however basically big your queued up Poisson is for it. So this will generate a random one for basically that lambda over that time frame. Yay, right? So that's the fast, easy way to get a Poisson variable. That's the Poisson concentration times, and then I've got my A for that pair box. Now, if you knew your particular A was always going to be a 0 or a 1, I wouldn't have to multiply it by this, because I explicitly checked to make sure that that's not 0. If it's always 0 or 1, I would have no words. Right? I left this in as a multiply because what if, based on my geometry, there was a reduced likelihood that it got out? Right? So maybe this is surrounded by bone or something like that. So this effect here allows me, if I in the future decide to add in a decay amount based on the geometry, to set how likely is this both photons actually to escape. And what I'd have to do is walk through the geometry for one and walk through it for the other, see how likely they both make it out, right? And I need both of them, so then I have to multiply those two probabilities of escaping, right? So if one has a 90% and the other has a 90%, right, it was dead centered and whatever, it wasn't too bad of an absorption on there, then I've got a net 81% chance that they both make it out. And I would then take that likelihood of absorption and I would multiply it by my A, was it on the path? So that now I've got something that tells me, was it on the path and how likely does it escape if it makes it? Right? But we said we didn't want So I originally wrote mine, so it did do it, but then I'm like, wow, it's way too complicated to have that other stuff, so I just didn't fit it. But I left this one in just as a note. If you want to include it, it's not conceptually bad to integrate it at this point. You just have to calculate those probabilities of escape, which is more like doing the entire, what we did for basically photon absorption in the initial one for X-ray, but partway through a body from different points. So it's just tedious. Anyway, in this particular case, as we're doing it, this multiply is unnecessary because of this check. And that we're only doing 0 or 1. We feel good? Okay. So that's it. It just adds them up. It does a particular random situation, figures out what it is, and away it goes. And boom, you now have pet data. Or at least simplified pet data. But it's at least legitimate for some particular situation. Good? Okay. Now, we technically have 15 minutes, so there's no way we're going to finish the next one, but we can actually kind of punk the next topic we have to do, and I do think this is somewhat helpful to actually talk about how are we going to solve this and just get us started. All right, so in essence now we're going the other direction. The first one we did there made up our fake data. All right. In real life, you wouldn't have to do that because you would just take your scanner and you would get the measurements. What you just wrote was a simplified fake the scanner. Right? But, for a variety of reasons, it's really hard to get actual pet data to give you. Number one, you have to get really big ones, so it's very slow when you're running it, unduly complicated. To take smaller amounts of measurements, it's radioactive, so I can't have you around when it happens, so I'm just handing you data, right? And it's not instructive, so that's why I kind of did the fake data. Now what we want to do is actually assume that your fake data thing was an actual machine, and it gives you the data, and it hands it off to you. Now you have to work back the other direction. Now, technically speaking, you get an A matrix, and you get a B matrix. And they're supposed to be related by A times the concentrations X is equal to B, or the concentrations times the lambda, or times the time factor, right, is equal to B. So I should be able to just take those, solve AX equals B, divide by the time factors, which is just going to be a uniform scaling, so you don't really necessarily have to even worry about that. But I should be able to just take AX equals B, put it in least squares, get an answer. Done. All right? If you do that, it will stink. Your answer will be horrible. Right? Part of the reason is when you look at this, it'll give you a warning message telling you your answer is going to stink because you're not going to have enough measurements here to actually accurately give you the answer. It's just, you won't. It's what's going to happen because of the structure and everything else. You're going to have insufficient measurements in this particular case. We make up for this when we're dealing with CT by doing more things and we do offset ones and everything else, but there's no way you can get enough here, right? You're going to have exactly as many equations as or pretty darn close to equations as unknowns if you're lucky, but it gets bins, so you might even have less. Even if it does happen from looking at the structure of the previous one, you might just want to run your code at like debug level 1 or 2. You'll see some of the, actually do it just for fun. Take the code you just run it. I don't care what you make the concentrations or whatever. Just set the debug equals to 1 so that you could see the patterning of this. And you'll see, and make it something like a, let's say like a 10 by 10. So it's a small image that's in there. And give yourself like 30 detectors. Right? And you'll see what I'm saying on this when you get it. You'll see big gaps. It'll make a pretty picture, but you'll get
some lovely gaps on this one.
Yeah, it looks lovely, doesn't it, right? Looks like a little work of art or something. But see how there's concentrated areas where they kind of combine up? You did different colors for different pairs and whatever, but see how there's rings and there's gaps? Remember how you got those rings, ring artifacts inside a CT, and it was like, why do I get that? Well, it's for the same reason that you're getting here. You just have less detector stuff off this one, so it's even more pronounced. But it's unavoidable to get those kind of ring artifacts in there when you're rotating. If we had the partial redo, it would break some of those rings up into semi-spirals. They technically be Lisa Joe figures, right, that are gonna, for each particular ring, so it doesn't completely get rid of them, but it spreads them out a little bit. And you would end up getting a little bit better, but that's even more complicated when you want to use it. But you can at least see the issue on this one. In addition, if you're considering this, right, a 10 by 10, and I gave you 30 detectors, right, you're gonna get 30 times 29 over 2. So you should have more detector pairs than there are unknowns, but you see the patterning, right? And a bunch of these things are kind of overlapping on which ones are in there, so it's going to be degenerate, right? How good is least squares when the data is degenerate? It's horrible. Yeah. So that's why it doesn't work. It's not that least squares is a bad technique. It's that given the situation that I've got, it stands no chance. It assumes you've got better data, basically. But in order to get better data under this case, it would cost outrageously more. I'd get more detectors. But for those more detectors to get enough counts to be reasonable, I got to up your radiation. So as I put in more detectors, I need more radiation for that to work on, which means I'm dosing my patients up. That's not a good solution to somebody who's got cancer, to give them unnecessary doses of radiation trying to find the cancer, because then I can't use it to treat it. I just gave it to your whole body, which meant everything got raised up, including your sensitive tissues and that. So to make this one so it's pretty enough that least squares would work, I would essentially have to dose my patient too high. It's just a bad trade-off. I can't do it. So now I need something that's going to allow me to add extra information to allow me to get maybe a grainy but an accurate grainy image. So I can use very low dose to find the cancer, so then I can go with a high dose thing to just kill the cancer. Right? This is one of those classic engineering trade-offs where we have to trade off on multiple things at different time periods because the variables all add up. Right? And that's partially what I love about medical imaging in a lot of these areas, because it's a life or death situation. That if we do it right, we can use our engineering skill to really make an impact on people. So, where there is challenge, there is great opportunity. So this is just a reminder of our expectation maximization, right? Expectation step, maximization step. That's going to be much harder to see in this one, because the expectation and the maximization, we're going to write it so it kind of falls into one equation, right? Because we're going to do the expectation and we're going to embed it into the maximization. You'll see it when we calculate some variables that contribute to one or the other, but we're going to write an update equation that's going to utilize this. And I'll show you why this happens, starting right here. Let's take a look at what's going on. Now, is anybody reading the book?
I didn't read this chapter.
I would encourage you to at least, there's like 2 pages on this. They use completely different names, but they do include a bunch of other stuff, and I kind of assumed you had. So they reference 9.36 in the book, which basically this is the likelihood function for a Poisson variable. And it basically looks like the likelihood is going to be equal to, we're going to sum up, right, over all of our different boxes that are out there, a situation where essentially what was the actual number of radioactive events that happened in that box. So let me just say over B, and this is boxes. The book uses N. I do not use N because it's not what the literature uses. So the book is trying to give you new variables that look kind of pretty, but then it doesn't correspond to anything in the literature. So I'm specifically trying to make mine correspond to the literature. So if you ever have to read an article, so I'm going to try to explain the connection between them when they go in. But this is the basic idea, right? N times the log of N bar, where N bar is your expected number of counts. This is kind of where we're going to get into that expectation area. You know, and then I've got plus N bar. And I'm going to do over these, right? So this likelihood, if I take its derivative with respect to that N bar, it's n equal to 0. This log gives me a 1 over n, so I'll get the n in this over the n bar. That one just becomes a constant. That becomes equal to 0. Take it to the other side. There's a differential ratio that comes out of this, right? Because this is n of something, a function, which is your concentration vector, right? So in our case, when I take the derivative with respect to it, I'm going to get this n, the b part first, nb over the n bar times this ratio of the f's, right? Ratio of f, right? Plus this, you know, getting basically your f's, the f's again. And I take it to, that's equal to 0. I take this to the other side, separate the ratios out, and I'll get basically a ratio of these times these gives me my update, right? Because I took that to the other side, right? That's basically what this equation is doing. The f in the book is lambda. So you can see there I've split the lambda ratio apart for this nicely. So I've got my new lambda for that particular box, and I'd have to do this for every box because it's a sum over that. But who cares? That's trivial, right? I in essence have my lambda for my box. My next estimate is lambda the previous times the ratio. And the reason why it's times the ratio is because the original equation, right, is n times log. It's different than your usual setup of it, right? This is a Poisson variable, not a Gaussian. So you're used to Gaussian structure. Well, Poisson, it comes in as a multiple. That's just trivially drops out of that equation. So you'll see it prettily written inside the book on 936. They don't tell you have to take the derivative and set it equal to 0. That's the one thing they give you that, and then they give you this in their own notation. And they say this works to solve it. And whenever somebody says that, it means it actually is a fairly straightforward thing. It's almost always take the derivative, set it equal to 0, and do a whole bunch of algebra to rearrange. So I just kind of did this to help you see where it was. And then since most of these variables mean nothing to you, I tried to give you what does the variable mean. So that's kind of what that second line is, right? So the first one is just to make the connection to this, right? That's that times this little ratio, which is the number count ratio.
Oh, is the second equation the same as the third?
And they're all the same.
Oh, I see.
I'm just adding more detail, right? So the thing that we saw from that is that the lambda update times some ratio, which is that NB, N bar stuff, right? You know, times a little ratio factor, things of that sort, right? Does that make sense? Okay. Yeah. So that's all I'm saying up there. It's that kind of ratio you get from taking this derivative. Right, now I'm substituting in. What is the ratio? Well, the ratio actually is, I have to take a look at what are all the detectors, the detector columns, every single one of them, right? What is their individual sensitivity to the particular box inside your solution you're trying to solve? And detector sensitivity is how likely, if there is a nuclear event that happens, that it finds it, right? So that sensitivity is going to be based on a whole bunch of things. Is it in line to even be able to produce it? If it's not in line, well, that's what we just calculated last time, right?
It's not a line, you can't see it. Right? If there's a large bone structure around it, it might absorb it and remove it. So it takes, basically, this idea of sensitivity is what we were calculating with that final A. Right? Remember I mentioned in there that A, we didn't worry about the absorption, but A really is not only your path, but it's are you on the path and how likely was something absorbed in there. So that number would be, did an event happen and how likely were both sides to be detected. So that's a sensitivity, right? My particular box could be located way on some offset someplace. So, if it's way on the outer extreme, there could be very few of these detector pairs that actually stand a chance of detecting this, right? So what we're saying with this is, for every detector pair possible, right, which is just summing up all the individual ones, right, how likely was I able to find this? That's what this denominator is, right? This is a particular detector pair. I might have to sum it up over each detector pair that's out there, right? One particular detector pair's sensitivity to that box times this ratio. This is the measured, what did you measure was the count along that line over what you expected to measure along that line. Does that make sense?
So is that expected detect count, is that gonna be like the Gaussian unit sigma that we're gonna be?
Yeah, except it's not going to be Gaussian,
Right.
it's Poisson, so it's a ratio.
Right.
That's the only thing I'm trying to
Okay,
get.
but that's the first step.
Yeah, yeah. So this is our expectation, which on the next slide I highlighted.
Okay.
But this is basically the expectation step, and then taking that expectation, plugging it in, the rest of it is the maximization.
Okay.
So it's one equation that does expectation and maximization all at once, right? And if I write in how to calculate these quantities, this is your B, but nobody calls it B, they call it Y, right? The Y is your data. If you're used to, our one person is taking controls, very often Y is your data, right? That's in, so it follows that type of idea. The sensitivities are P's because they're probabilities that box B events are detected by detector pair D. So that's why it's, in the literature, it's called P because it's a probability that that's detected. But it means sensitivity, in the book uses sensitivity, but that sensitivity is a probability. So that's why it's P's in these spots where the sensitivities are. My expected detector count is lambda is how likely an event happens. So lambda times the probability that that event gets detected summed up says how likely was something in that box detected, right? And this is what really was detected, what did I think was going to be detected. So if more things were detected than I thought with my current idea of the concentration, this number is bigger than 1. So when I'm multiplying, this grows. And this is just a weighted thing of this ratio. So that makes this one bigger than this, which makes lambda grow. Right? If there was less of these than these, this is smaller, it makes an individual component from here shrink. So therefore the overall ratio will be smaller, which makes you shrink the appropriate lambda quantity. So if you think of it in those terms, it makes total sense. We do it as a ratio multiplication because that's the correct thing for a Poisson distribution when you take a look at the likelihood. It's ratios, right? Whereas with Gaussians, it's additions. Okay? We often do Gaussian because it's easier, because addition is easier than multiplication, subtraction than division. But that's all we've switched to. When we go to Poisson, it's multiply and divide, not add and subtract. Right? So this is basically the same thought of an equation, just turned from the plus minus spectrum to the times divide. Does that make sense? Right? That's all it is. And the next slide, all I said was I just did exactly what you noted. The expectation is the goal box. Right? And the rest of it is maximization. So alls we're gonna do is write code to basically do this equation on all the data and then iterate over and over again for each box detector pair, and we'll get an idea of better concentration. It should converge, we should get an answer. And it should be able to handle much smaller and less numerically stable stuff. Cool. Well, we're gonna stop there. We'll pick up next time. So have a lovely weekend. See you all on Tuesday or before if you so wish.